Imagine standing in the middle of the largest known void in the universe, a region roughly 330 million light-years across, in which almost nothing exists. From the center, with the unaided eye, the night sky would be a uniform black. No stars, no galaxies, just dark. That view, it turns out, is what most of the universe looks like. Most of cosmic volume sits inside voids, like that, and we sit, briefly, inside one of the small, warm exceptions. Tonight, we're going to find out why the universe is shaped this way, what is hiding in all that nothing, and why some physicists, when they look at the math, find the answer slightly terrifying. Get comfortable, settle in. Part 1. A hand on a table. Reach out, if you can. Put your hand on the nearest hard surface. The table you're sitting at, the arm of the chair, the edge of your bed, the wall behind your pillow. Press down. Feel the resistance. Feel the way your fingers stop moving when they reach the wood, or the metal, or the fabric, or the plaster. Feel how completely solid that surface is, how decisively it refuses to let your hand pass through. I want you to remember that feeling. Hold it in your mind, just for a moment, because over the next 2 hours, very slowly, very carefully, I am going to take that feeling apart. I am going to show you that what you just felt was not what you thought it was. I am going to show you that the surface under your hand, and the hand itself, and the room around you, and the planet under the room, and the sun warming the planet, and the galaxy holding the sun, and the cluster holding the galaxy, and the universe holding the cluster, are all built around the same secret. They are all, almost entirely, nothing. The title of this video makes a claim, and I want to say it out loud before we go any further, because the rest of tonight is an argument for it. The universe is empty by design, and it is horrifying. Both halves of that sentence are doing real work. Empty, I mean almost literally. By any honest measure of volume, the universe is, to a precision that should make you slightly dizzy, made of nothing. By design. I do not mean by anyone's plan. I mean that the emptiness is not a leftover, not a glitch, not a coincidence. It is built into the equations that make existence possible. Without it, atoms could not hold their shape. Stars could not burn. Time, as we know it, could not move. The emptiness is the architecture, and horrifying is the part you can argue with. I'll let you decide, by the end, whether it earns the word. Let me sketch the road ahead. We are going to take a long, slow walk tonight, from the inside of a single hydrogen atom outward, through the body that contains it, through the room and the planet, and the orbit and the solar system, out past the heliopause, past the Oort cloud, across light years of empty space to the next star, and then onward to the spiral of the Milky Way, with its hundreds of billions of suns and a 5 light-year average gulf between them. Then out further still, past the local group, past the Virgo supercluster, into the cosmic web, where galaxies hang on threads in a structure that has been mapped, this year, with more detail than any year before. We will pass through the largest known voids regions, hundreds of millions, even billions, of light years across, where almost nothing exists. We will examine the cosmic inventory, and we will discover that 95% of the universe is not made of anything we can see or touch. We will go inside the so-called empty space itself, and find that empty is the most active state in physics. And we will follow the trajectory of all this emptiness forward in time, into a future where the architecture wins, and the structure thins, and the lights go out, slowly, one by one. By the end, you will have an answer to the question the title asks. You will know what empty by design means. You will know why some physicists, when they look at the math, find it slightly terrifying. You will know what is sitting under your hand right now. And you will know, I hope, why this is also one of the most extraordinary things to ever be true. Before we begin, a few small things. Get comfortable, settle in. There is nothing to worry about tonight. We are going to move slowly. We are going to take our time. You are not being asked to follow anything difficult. You are being asked to come along on a walk. 2 telescopes earlier this year, the James Webb Space Telescope and a survey called DESI, released the most detailed maps of cosmic structure ever made. We will visit both. They show the same thing. They show emptiness, beautifully and patiently rendered. A hydrogen atom, the simplest atom in the universe, 1 proton and 1 electron, is more than 99.9999999999996% empty by volume. If you took a hydrogen atom and scaled it up to the size of the Earth, the proton at its center would be roughly 200 meters across a single skyscraper at the core of an entire planet. The electron would be a faint probability cloud somewhere near the surface. Everything in between would be nothing, and yet that atom multiplied by some 7 times 10 to the 27th of its siblings is what your body is made of. You are mostly nothing. The table is mostly nothing. The chair you're sitting in is mostly nothing. The sensation of solidity you are feeling right now, the very thing that makes your hand stop at the surface, is not contact. It is something stranger. The reason your hand stops and does not pass through is that the electrons in your fingertip are encountering the electrons in the surface, and the 2 clouds of probability are refusing to share space. They cannot share space. They are forbidden by a rule of quantum mechanics so strict that physicists call it a principle from occupying the same quantum state. The refusal generates a force. The force feels, to you, like a wall. You have never actually touched anything in your life. You have only ever come close. The closest you have ever come to anything is about a few tenths of a nanometer. The rest is repulsion across a gap. The solidity of the world is a courteous fiction maintained by the rules of fermions. If those rules failed, if the exclusion principle stopped working, even for a moment, every atom in your body would collapse to the size of its nucleus. Every solid object in your house would shrink to a pinpoint. The Earth would become a sphere the size of an orange. All 8 billion human beings, condensed by the failure of exclusion, would fit inside a single sugar cube. We will get to that idea, with calm and care, in a few minutes. But first, I want to plant one more thought, because it is going to come back near the end of this video, and I want you ready for it. There is a number in physics. When researchers calculate the energy that should be present in completely empty space, the energy that the rules of quantum field theory predict must exist in even the most perfect vacuum, they get a result that is wrong. By comparison with what we actually measure, by a factor of 10 to the 120th. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in the history of science. The vacuum is hiding something. We do not know what. I tell you this now, so that as we walk through all the layers of emptiness in the universe, you'll know that the very last layer, the smallest scale, the bare quantum vacuum, is not just empty. It is precisely tuned to values that no current theory can derive. That is the core of what by design means. Somebody, or something, or some principle we have not yet identified, has set the emptiness to exactly the value it has to be in order for us to be sitting here. Move that value by a small amount in either direction, and there is no one to notice it has moved. So keep your hand on the table. Keep that feeling of solidity in your mind. We are going to take it apart, layer by layer, scale by scale, until you can almost see through your own hand. And then we are going to go further, because the floor under that table is, itself, almost entirely nothing. And so is the planet under the floor. And so is everything else. Where would you like to start? I'd like to start inside the atom. The first vacuum on the road ahead is the smallest one. It is the one you can feel right now, under your fingers, pretending to be a table. Let's go in. Is less than break time equals 1s is greater than number part 2. Inside the smallest vacuum in the world. When we say the atom is empty, we are not being poetic, we are being precise. And the precision is important because the number itself is so enormous that anything less than precision makes it sound like exaggeration. A hydrogen atom, the simplest atom in existence, consists of one proton and one electron. The proton sits at the center. The electron occupies a region around the proton, what physicists call the orbital. The orbital is not a path. The electron does not orbit the proton the way a planet orbits a sun. The electron exists, mathematically, as a cloud of probability, a fuzzy haze that defines where the electron is likely to be if you were to make a measurement, but not where it actually is in between measurements. In a very real sense, between measurements, the electron is not anywhere at all. It is everywhere it might be, weighted by probability. The volume occupied by that probability cloud, measured from the proton outward, is about 10 to the negative 10th meters in radius, about 1 angstrom. The proton at the center is about 10 to the negative 15th meters across. That is a difference of 5 orders of magnitude, a factor of 100,000. The proton occupies, by volume, about 1 part in 10 to the 15th of the atom, which means that the atom is, by volume, about 99.99999999999% empty. Let me put that into a picture that you can hold in your head. Imagine a hydrogen atom scaled up so that the entire atom is the size of the Earth. The atom is now 12,742 kilometers, across the same as the planet you're standing on. What about the proton at its center? Where is the proton? The proton, at that scale, is about 200 meters across, about the height of a single tall skyscraper. Sitting at the center of an entire planet, everything between that 200-meter skyscraper and the surface of the planet is empty. There is no air. There are no buildings. There are no other particles. There is, by any meaningful measure, nothing in between. The electron is a smear of possibility, mostly out near the surface, mostly nowhere in particular, but never inside the skyscraper at the center. That is one hydrogen atom. Your body contains around 7 times 10 to the 27th of them. Each one of them is built like that. Each one of them is, at its very core, a tiny solid kernel of mass inside an enormous volume of nothing. If you removed all the empty space from your body, if you took every atom and collapsed it down so that only the protons and neutrons remained, packed together as tightly as they will go, what's left would not be visible to the naked eye. The mass would be roughly the same. The volume would be roughly the volume of a grain of dust. The condensed version of you would weigh 70 kilograms and fit on the head of a pin. The entire human population of the planet, about 8 billion people condensed the same way, would fit inside a single sugar cube. Same total mass. Volume, about 1 cubic centimeter. The matter exists. The volume is mostly an illusion. We know all of this in a precise empirical way because of an experiment performed in 1909 by Ernest Rutherford in collaboration with Hans Geiger and Ernest Marsden at the University of Manchester. At the time, the prevailing model of the atom, the so-called plum pudding model, proposed by J.J. Thomson, held that an atom was a uniform sphere of positive charge with electrons embedded in it like raisins in a cake. The atom, in the plum pudding model, was solid all the way through. There was no empty space inside it. Rutherford set out to test that model by firing alpha particles, small, positively charged nuclei, basically helium without its electrons, at a thin sheet of gold foil. He expected almost all of the alpha particles to pass through the foil with only the slightest deflection. the way a bullet would pass through a bowl of soup. Most of them did. But every so often, about 1 in 8,000, an alpha particle came bouncing back, almost straight back the way it came. Rutherford famously said it was as if you had fired a 15-inch shell at a piece of tissue paper and the shell had come back and hit you. The conclusion was that nearly all the mass of the atom was concentrated in a tiny region at the center. The rest of the atom was empty, empty enough that nearly all the alpha particles sailed right through. The atom was not a pudding. It was a near-perfect vacuum with a small, dense core. That experiment is the origin of every modern picture of atomic structure. It is why the atom in your textbook has a nucleus at the middle and a void around it. It is why you have known, since some moment in childhood, that atoms are mostly empty space, even if no one ever showed you just how empty. The next obvious question is the one a child would ask. If the atom is mostly empty, what keeps the electron from falling into the nucleus? The proton has a positive charge. The electron has a negative charge. Opposites attract. By the rules of classical electromagnetism, the electron should spiral inward, radiating energy as it goes, until it collapses into the proton in a very short fraction of a second. Atoms, according to classical physics, should be unstable. They should not exist at all. They exist because classical physics does not apply at this scale. Quantum mechanics does, and quantum mechanics has rules that prevent the collapse. The first rule is the Heisenberg uncertainty principle. It says that the more precisely you know where a particle is, the less precisely you can know its momentum, and vice versa. If you tried to localize the electron tightly to the proton, to force it into the tiny volume of the nucleus, the uncertainty in its momentum would skyrocket. That momentum corresponds to energy. The energy required to confine the electron that closely is more than the entire system has available, so the electron cannot, in principle, occupy that volume. It is held out at a certain minimum distance by the cost of its own confinement. The second rule is that the energy levels available to the electron are quantized. The electron cannot occupy any arbitrary distance from the proton. It can only occupy specific orbitals, each at a specific energy. There is a lowest possible orbital, the ground state, below which the electron cannot go. The atom has, mathematically, a floor. The floor sits at 1 angstrom. The electron rests there, and nowhere closer. The third rule, which we'll come back to in the next part because it is the deepest and most strange, is the Pauli exclusion principle. It says that no two electrons in the same system can occupy the same quantum state at the same time. This rule does not affect hydrogen very much. Hydrogen has only 1 electron, but it has enormous consequences for every other atom in the periodic table, and for every solid object in the universe. We will sit with it in a minute. For now, what I want you to feel is this. The emptiness inside the atom is not just present, it is required. It is held in place by 3 layers of quantum law. The atom is empty because it would not be stable any other way. Take away the uncertainty principle, and the atom collapses. Take away quantization, and the atom collapses. Take away exclusion, and every atom heavier than hydrogen collapses. The emptiness is structural. It is the precondition for everything else. There is a quieter discovery, more recent, that I want to mention in passing, because it is one of those facts that makes the picture even stranger. At the Large Hadron Collider, physicists can resolve structure inside the proton itself. The proton, which is the dense solid kernel at the center of every hydrogen atom, the central kernel of our whole emptiness story, turns out itself to not be entirely solid. It is a roiling, restless thing made of 3 valence quarks bound by gluons, surrounded by a sea of virtual particles popping in and out of existence. Most of the proton's mass is not in the quarks. Most of the mass, about 99%, comes from the binding energy of the gluon field. Even the solid part of the atom is, in a sense, made of field activity rather than discrete substance. Even the part that bounced Rutherford's alpha particles back is, when you look closely enough, mostly process. Mostly something happening rather than something being. But that is a thread for later. For now, what matters is that your body is mostly nothing. The table is mostly nothing. The wall is mostly nothing. And the reason none of it falls in on itself, the reason the matter holds its shape, is one of the most extraordinary principles in all of physics. So let's go meet it. Let's go find out why your body does not collapse, and what would happen if it did. Is less than break time equals 1s, is greater than number. Part 3. Why your body doesn't collapse. The Pauli exclusion principle was first articulated by Wolfgang Pauli in 1925. It is one of those discoveries that sounds, at first, like a piece of mathematical bookkeeping, but turns out to be holding up the entire physical world. Without it, the universe we know does not exist. The principle is simple to state. No two electrons in the same quantum system can occupy the same quantum state at the same time. By quantum state, we mean the complete set of quantum numbers that describes an electron, its energy level, its angular momentum, its orientation, its spin. Two electrons can have the same energy level if they have opposite spins, but two electrons in the same place, with the same energy, with the same spin, that is forbidden. Not just unlikely, forbidden. The consequences of this rule are everywhere. The reason atoms have shells, the reason the periodic table has the structure it does, the reason carbon bonds the way it does, the reason iron is iron and gold is gold, is the Pauli exclusion principle. Electrons fill the available quantum states in a system from the lowest energy up, like passengers boarding a train and taking seats one by one. They cannot all sit in the cheapest seat. The cheapest seat fills up. The next electron has to take the next cheapest. The atom's shape, its electron shells, its bonding behavior, its chemistry, is the result of electrons obeying that boarding pattern. Now consider what would happen if the principle failed. Imagine, for a moment, that electrons could share quantum states. Imagine that the rule went away. Every electron in your body would immediately fall to the lowest available energy state. There would be no shells, there would be no orbitals. There would just be a swarm of electrons piled up against the nuclei, packed as close as classical electromagnetism would allow. The atoms would shrink to the size of their nuclei. The space inside every atom, the 99.999% void that gives matter its volume, would disappear. Your body, in that scenario, would collapse instantly, not to a smaller human-shaped body, not even to a human-shaped object that's denser than usual. It would collapse to a kernel of nuclear matter. The mass would not change. The volume would. You would become a drop of neutron star material, roughly the size of a single grain of sand. The kinetic energy released by that collapse would, incidentally, be enormous, but never mind that for the moment. The same thing would be happening to everyone else, all around the world, simultaneously. Every human being, every animal, every plant, every tree, every cloud, every building, every continent, every ocean. The Earth itself would collapse its 8,000 kilometers of radius, shrinking, in a fraction of a second, to a ball about the size of an orange. The orange would still weigh 6 times 10 to the 24th kilograms. It would just be much smaller, 6 sextillion tons in your hand. Most of what we call the Earth, it turns out, is empty volume held open by quantum law. Take away the law, take away the volume. The 8 billion human beings on the planet, condensed the same way, would fit inside a single sugar cube, 1 cubic centimeter, holding the entire population of the species. We would weigh, altogether, about 480,000 metric tons. We are mostly the spaces between our own atoms. This is not science fiction. This is what the math says, and the math has been tested. The reason it doesn't happen is that Pauli exclusion is one of the most reliable rules in all of nature. We have never observed a violation. We do not know how to make one. The rule appears to hold absolutely. There are physical systems, like white dwarfs and neutron stars, where Pauli exclusion is the only thing holding gravity off the so-called degeneracy pressure of the squeezed fermions resists further collapse. In a white dwarf, it is the electrons whose exclusion holds the star up. In a neutron star, it is the neutrons. In both cases, the principle is doing real, measurable, structural work. We see it in the masses of the stars. We see it in the radii. We see it in the timing of pulsars. It is, in every test we have devised, an iron law. Now I want to come back to what your hand is doing on the table. Because once you understand exclusion, you understand touch. When you press your finger to the surface, the outermost electrons in your skin approach the outermost electrons in the surface. As they get close, two things happen. The electromagnetic force between them gets stronger. They repel each other with the inverse square law of like charges. And at the same time, the Pauli exclusion principle kicks in. The electron clouds resist being forced into the same quantum states as their counterparts in the surface. The combination produces an enormous resistance to further compression. Your finger stops. The surface holds. The two electron clouds maintain a gap between them of about a few tenths of a nanometer. That gap is, in a sense, the actual location of the table. It is the surface of the resistance. It is the meeting place of the two refusals. Notice what is missing from this story. The protons in your finger do not touch the protons in the table. The neutrons do not touch the neutrons. The atoms do not touch the atoms. None of the matter actually meets any of the other matter. Everything stays in its own quantum state, held apart by repulsion and by the prohibition on sharing. The sensation you call contact is the sensation of being refused. I would like to repeat that sentence in case it slipped past. You have never touched anything in your life. You have only ever come close enough to be refused. The closest you have ever come to your phone, your partner, your child, your own face, is a few tenths of a nanometer. The touch you feel is the refusal of two clouds of probability to share the same space. The world feels solid to us because the refusal is consistent. We have learned, since infancy, to interpret the refusal as the presence of stuff. But what's there is not stuff. What's there is law. Now I want to bring us back to the central claim of tonight, because we have just earned the first piece of it. The emptiness inside the atom is enforced. It is not a happenstance configuration. It is the result of quantum rules, the uncertainty principle, the quantization of energy, the exclusion principle working together. Each of those rules is precisely what it is. Each of those rules holds open a precise amount of volume. If any of the rules were different, the matter we know would not be possible. The emptiness inside the atom is, in the most literal sense, by design. The design is encoded in the equations of quantum mechanics. The encoding is non-negotiable. Take the rules, take the emptiness, take the emptiness, take the matter. We have now walked through the first scale of cosmic emptiness, the inside of the atom, and we have discovered that it is structural, enforced, and required. The atom is empty because it has to be. The body is empty because the atom is. The table is empty because the body is. The floor is empty because the table is. Everywhere you look at this scale, the void is not the absence of something. It is the precondition for something. If that is true at the scale of the atom, what is it like at the scale of the room, the planet? The orbit? The solar system? Is the same secret hiding there too? Is the void scaling up with us? The answer is yes. Spectacularly yes. And the gulf, once we step outside the body, gets much larger. Take a breath, settle in a little further. We are leaving the planet now. Not to look back at it from above, we'll do that another night, but to look at what is between it and the next planet, and the next, and the next. Is less than break time equals 1s is greater than. Number, part 4. The solar system is mostly distance. Step outside, in your mind, and look up. Find a point of light in the sky and ask, calmly, how far away it is. If the point is the moon, it is about 384,000 kilometers from where you stand. If the point is Mars, it is somewhere between 55 million and 400 million kilometers, depending on where the two planets are in their orbits. If the point is Saturn on a clear night, it is around 1.5 billion kilometers away. If the point is one of the very faintest stars you can see with the unaided eye, it is most likely between 40 and 500 light-years away. Notice what happens to the numbers as we move outward. They get bigger fast. They get bigger in a way that human intuition is not prepared for. Our brains evolved to understand distances on the African savanna. They are not built to handle the gaps between planets, much less the gaps between stars. So, we are going to do this carefully. We are going to build a scale model in your mind, and then we are going to walk through it. Begin with the Sunday. Shrink the sun, just for the purposes of this thought experiment, down to the size of a basketball, about 24 centimeters across. Hold it in your imagination at the front of a large room. Now, where is Earth? Earth, at this scale, is a small p, about 2 millimeters across, sitting 24 meters from the basketball. That is the size of a large auditorium. If the sun is at the front of the auditorium, the Earth is a small p sitting in the back row. Between the basketball and the p, what is there? Nothing. A thin scattering of solar wind plasma. Some passing meteoroids. A handful of artificial satellites. Otherwise, nothing. 24 meters of empty space. That is the most populated part of our solar system, by the way. That is the inner orbit, the part where Earth lives. Now, keep walking. Mars, in this model, is about 36 meters from the basketball. The asteroid belt, at its midpoint, is around 80 meters out. Jupiter is 125 meters away, about the length of a city block. Saturn is around 240 meters out. Uranus is half a kilometer away. Neptune is 3/4 of a kilometer from the basketball at the front of our auditorium. And between every one of those distances, meters, tens of meters, hundreds of meters, there is, by any meaningful measure, nothing. The planets themselves are small. Jupiter, the largest of them, would be a marble about 25 millimeters across in this model. The rest are smaller. The total mass of all the planets combined is less than 0.1% of the mass of the Sunday. Almost everything you call the solar system is the sun, and almost everything else is the gap between the sun and the next interesting thing. To get a feel for these gaps in real units, consider Voyager 1, which launched in 1977. It is the fastest probe humanity has ever sent away from the sun on a permanent trajectory. As of this year, 2026, it has been travelling for nearly 50 years. It is now beyond the heliopause, the boundary where the sun's wind gives way to the interstellar medium, at about 160 astronomical units from the Sunday. An astronomical unit is the distance from the Earth to the Sun, 150 million kilometers. So Voyager is now about 24 billion kilometers away, after 50 years of unbroken motion through almost nothing. If you were to keep going past Voyager, past the heliopause, you would enter the Oort cloud, a theoretical shell of icy bodies, thought to extend from somewhere around 2,000 astronomical units out to about 100,000 astronomical units. That outer edge is about 1.5 light-years from the Sunday. Voyager, travelling at its current speed, would take roughly 40,000 years to reach the inner edge of the Oort cloud, and about 300,000 years to reach the outer edge. And the outer edge of the Oort cloud is not even halfway to the next star. Proxima Centauri, our nearest stellar neighbor, is 4.24 light-years from the Sun. At Voyager's speed, the trip would take around 75,000 years. At light speed, it would take 4 years, 2 months, and 10 days. To put that into the basketball and pea model, if the Sun is a basketball at the front of the auditorium and Earth is a pea 24 meters away, then Proxima Centauri is a tennis ball roughly 7,000 kilometers away. 7,000 kilometers, in the scale model where the Sun is a basketball. That is the distance from a basketball court in New York to a tennis ball in Paris. Between those two balls, in our scale model, there is nothing for 7,000 kilometers. Nothing at all. A few hydrogen atoms drifting in interstellar space, perhaps 1 or 2 per cubic centimeter. The occasional micrometeoroid, the cosmic ray flux. Otherwise, empty. That is the texture of the solar neighborhood. That is what surrounds us. We live inside an enormous quiet, a near-perfect vacuum studded with the very occasional star and the very occasional planet around the very occasional star. I want to drop in a number, because the number is one of those things that I find myself returning to often when I think about cosmic emptiness. The average density of matter in interstellar space in our region of the Milky Way is roughly 1 atom per cubic centimeter. The very best vacuum chamber on Earth, the kind used in semiconductor fabrication or in some particle physics experiments, has a residual density on the order of 10,000 particles per cubic centimeter. The space between the planets in our solar system is, by that measure, 10,000 times emptier than the emptiest place humans can make on the surface of the Earth. And the space between the stars is emptier still. We cannot make a vacuum down here as good as the one outside our front door. So when we say that the universe is mostly empty, we are not saying it loosely. We are saying that the very best emptiness we can construct in a laboratory is much, much, much less empty than the casual default state of the solar system. We are saying that the gap between Earth and the Sun is a better vacuum than anything humans have ever built. We are saying that the line between the planets is not a line through stuff with a little nothing in between. It is a line through nothing with a little stuff in between. I want to come back to the central thread for a moment, because the picture is starting to come together. The atom is empty by design, held open by quantum rules. The solar system is empty by the rules of gravity and the way matter coalesces. Mass collects locally into stars and planets, and the gas that doesn't collect is dispersed by the star's radiation and wind. The gravitational geometry leaves enormous gaps. The gaps are not waiting to be filled. The gaps are the basic configuration. Stars and planets are, in this sense, condensation droplets in a much larger volume of nothing. If the inside of the atom is empty by quantum law, the inside of the solar system is empty by gravitational geometry. Both are required outcomes of physical rules. Both are structural. Both are the precondition for the kind of universe in which the kind of structures we know can exist. If matter clumped less, we would have no stars. If matter clumped more uniformly, the universe would be a fog with no objects in it and no light. The emptiness between objects is what makes objects. This is the second scale of cosmic emptiness. We have now climbed from the atom, through the body, through the room, through the planet, into the orbit, and out to the heliopause. We have seen that the void scales upward with us. We have seen that at every step, the void is not a gap in the structure, it is the structure. The next step is bigger, much bigger. The Milky Way is 100,000 light-years across. It contains hundreds of billions of stars. From a great distance, it looks like a thick disk of light. From inside it, which is where we are, it looks on a clear night like a band across the sky. But the band of light is, like everything else we have seen tonight, mostly a long-exposure illusion. The galaxy is mostly the gaps between the stars. And the gaps are, on average, 5 light-years across. Let's go. Is less than break time equals 1s is greater than number, part 5. A galaxy is mostly sky. Picture the Milky Way as you have seen it in photographs. A flattened spiral with arms curling outward from a central bulge lit by hundreds of billions of stars. About 100,000 light-years from end to end. About 1,000 light-years thick at the disk, surrounded by a fainter halo of older stars and dark matter. A glowing pinwheel against a black background. Now I want to take that image away from you, gently, because it is the wrong picture. The Milky Way is not glowing. The Milky Way is, by volume, almost entirely dark. The light you see in photographs is the integrated emission from a few 100 billion stars spread across a volume of roughly 4 trillion cubic light-years. Most of that volume contains no star. Most of that volume contains nothing at all. The photographs work because we average together billions of years of starlight from billions of objects and compress the result into a single frame. What you see is a statistical fiction, true in its way, but false to the experience of being there. Consider a more honest version of the same picture. The Milky Way is a region of space about 100,000 light-years across, in which the average distance between neighboring stars is around 5 light-years. In the solar neighborhood, the density is about 0.1 stars per cubic parsec, about 1 star for every 10 cubic parsecs of volume. A parsec is about 3.26 light-years. So in a cube of space, 10 light-years on a side, you would expect to find, on average, 1 star. And around that star, for 5 light-years in every direction, there would be nothing of comparable mass. Just a thin scattering of hydrogen, perhaps 1 atom per cubic centimeter, some cosmic dust, a few molecules in the densest clouds. Otherwise, dark, quiet, cold vacuum. If you shrank the sun down to a grain of sand, the rest of the Milky Way at that scale would still be roughly 3,000 kilometers across. The galaxy would be a handful of sand spread across the continent of Africa. 1 grain in Cairo, the next grain in Lagos, the next grain in Cape Town, with nothing between them, a starship traveling at the speed of light, plotted from the sun to the galactic center, would take about 26,000 years. Most of that journey would be spent passing through nothing. Occasionally, the ship would brighten as it crossed close enough to a star for its light to dominate the view. Mostly, it would be dark. Mostly, the windows would show a few distant pricks of light in an otherwise unbroken black. I find this fact moving in a way I struggle to articulate. The Milky Way looks like a river of light to us because we are looking edge-on through 100,000 light-years of disk. The brightness is an accumulation. It is the same trick that makes a forest look continuous from a distance and reveals itself as mostly clearings only when you walk into it. Step into the Milky Way at any point, and the forest is mostly clearing. The trees are 5 light-years apart. The trees are very far apart indeed. Let me ground this in a piece of recent science. Earlier this year, in 2026, a team at the University of California, Riverside, working with data from the James Webb Space Telescope, released the most detailed map ever made of cosmic structure. The map, called Cosmos Web, charts 164,000 galaxies across 13.7 billion years of cosmic history. It is one of the largest single survey results of the JWST era. But here is the part that matters for our story tonight. 164,000 galaxies sounds like a lot, until you realize the volume the survey covers. The map captures a small fraction of the observable universe. Even within that fraction, the galaxies are tiny dots of light, separated by enormous tracts of dark space. The most detailed map of cosmic structure ever produced is, when you take a step back, a map of how the bright things are arranged inside an overwhelming amount of nothing. A second result, also from 2026, made the picture even more vivid. In March of this year, astronomers published the first ever direct image of glowing hydrogen along cosmic web filaments at redshifts of 9 to 11 billion years ago. For the first time, we had a photograph, not a simulation of the threads through the dark. The image shows the threads. It also shows what's between them. What's between them is the answer to everything we've been talking about. Most of the volume of the universe is between the threads. Inside our own galaxy, the same pattern applies. The disk is not uniform. It has spiral arms, where stars are more concentrated. It has dust lanes. It has molecular clouds, the densest regions in the galaxy. In the densest cores of those clouds, the so-called stellar nurseries, the density rises to about 1 million particles per cubic centimeter. That sounds like a lot. By cosmic standards, it is. By terrestrial standards, it is still emptier than the best vacuum chamber on Earth. A molecular cloud is a place so dense that stars can form in it. The same place is, by laboratory standards, a vacuum. This is one of the recurring lessons of the night. What looks dense from a long way away is sparse up close. What looks like substance is mostly distance. The Milky Way is not a glowing disk of stars. It is a thin scatter of stars in a much larger volume of mostly nothing. I want to mention, in passing, the lesser-known fact that our region of the galaxy is unusually empty even by galactic standards. The Sun sits inside a structure called the local bubble, a roughly 1,000 light-year-wide region of space cleared out by a series of supernovae that detonated several million years ago. The local bubble has even fewer atoms per cubic centimeter than the average interstellar medium. We are, in other words, in a bubble of relative emptiness within a galaxy that is itself overwhelmingly empty. The emptiness, here, is fractal. Each time you zoom in, you find smaller, even emptier regions inside the bigger ones, and we live near the center of one of them. The thread continues, undisturbed. At the scale of the atom, emptiness is enforced by quantum law. At the scale of the solar system, emptiness is enforced by the geometry of gravitational collapse. At the scale of the galaxy, emptiness is enforced by the simple fact that mass collects locally and leaves enormous tracts of vacuum between collection points. At every scale, the same pattern. Mass clusters. Vacuum dominates. Order arises in pinpoints. Disorder, in the sense of the lack of accumulation, fills the rest. If the galaxy is mostly nothing, what is between the galaxies? What does the universe look like when you zoom out far enough that the entire Milky Way is just one more pinprick of light? Here is where the story gets, in my opinion, the strangest and most beautiful, because at the largest scale we can survey, the pattern reaches a kind of crescendo. There are voids out there that make the Botas star fields look crowded. There are gaps so large that if you stood in the middle of one of them and looked out at the sky with the unaided eye, you would see nothing. No stars, no galaxies, just dark. Just the cosmic background, stretched too long to be visible to your eyes. Just a vault of black. And we possibly live near the center of one of those voids. Let's go and see. Is less than break time equals 1s is greater than number part 6. The map of the universe is a map of holes. In the late 1970s, astronomers began noticing something strange about the distribution of galaxies in the sky. The galaxies were not, as had been quietly assumed, spread out more or less uniformly. They were clumped. They were strung along filaments. They were grouped into clusters. And between the clusters, there were enormous regions of sky containing very few galaxies, sometimes none at all. In 1981, the astronomer Robert Kirshner and his collaborators identified the first of the great cosmic voids in the direction of the constellation Botes. The void was about 330 million light-years across. To put that into context, the Milky Way is 100,000 light-years across. The Botes void is 3,300 times wider than our entire galaxy. If you placed the Milky Way at the center of the Botes void, you would not see another galaxy, even with a powerful telescope, until the edge of the void. The galaxies inside the void are very few, and they are widely separated. From the center, with the unaided eye, the night sky would be black. Let me sit with that for a moment, because it is the kind of fact that takes a while to land. If our Milky Way had formed inside the Botes void, instead of where it is, the entire history of human astronomy would be different. We would not have noticed other galaxies until the 1960s, when our telescopes finally got big enough to see across the void. For 3,000 years of recorded history, we would have looked up at a sky that contained our own galaxy and nothing else, and we would have concluded, with strong evidence, that the universe was a single, isolated island of stars surrounded by an infinite quiet. Most of cosmic real estate has exactly that view. The Botes void turned out to be only the beginning. As surveys improved through the 1990s and the early 2000s, more and larger voids were found. The cosmic web came into focus. The universe, it turned out, was not a uniform sea of galaxies. It was a foam. Galaxies sat on the surfaces of bubbles. The bubbles were filled, very nearly, with nothing. The walls of the bubbles met at edges, the edges met at corners, and the corners were the densest clusters of galaxies in the observable universe. Most of cosmic volume sat inside the bubbles. The bubbles were enormous. The bubbles were almost everything. In 2007, a team led by Lawrence Rudnick at the University of Minnesota studied the so-called cold spot in the cosmic microwave background, a region of the sky where the leftover radiation from the early universe is slightly cooler, average. The team proposed that the cold spot might correspond to an enormous void. In 2015, a follow-up study using galaxy surveys identified what may be the Eridanus supervoid, a region roughly 1.8 billion light-years across. That is more than 5 times the diameter of the Botes void. The size has been debated, but if real, the Eridanus supervoid is the largest structure ever identified in the universe, and it is a structure made of nothing. A few years before, in 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, published a paper proposing that we ourselves might sit inside a giant cosmic underdensity, a void about 2 billion light-years across. Their name, abbreviated, gives us the KBC void. The proposal was that the Milky Way and the entire local group sit roughly near the center of an enormous underdense region, a hole in the cosmic web large enough to contain a substantial fraction of the observable universe. The KBC void is contested. The data are not yet conclusive, but the case has only grown stronger in the years since. Our local measurements of galaxy density at increasing distances from us seem to show that the density rises as we move farther out, exactly what we would expect if we were near the center of an underdensity. The peculiar velocities of local galaxies seem consistent with the gravitational pull of more massive structures outside our local volume. The picture, while still uncertain, is one in which our entire civilization sits inside an enormous emptiness near the middle of one of the largest holes ever found. If this is correct, then a quietly remarkable thing follows. Light that reaches us from outside the KBC void has been traveling, on average, through space that expanded slightly faster than the cosmic average, because regions outside an underdensity participate more strongly in the overall Hubble flow. That faster average expansion can make the local Hubble constant, the rate of expansion measured nearby, appear higher than the global one. The so-called Hubble tension, the puzzling disagreement between local and cosmic microwave background measurements of the expansion rate, currently around 5 sigma, might be partly geometric. It might be partly an artifact of where, in the emptiness, we happen to live. Now consider what JWST has revealed this year. The Cosmos Web Map, published earlier in 2026 by the team at UC Riverside, traces 164,000 galaxies across 13.7 billion years of cosmic history. The map reveals the dark matter scaffolding of the universe at higher resolution than anything before it. The scaffolding is filamentary. The filaments are thin. Between the filaments are voids. Voids dominate the picture. A second result: the March 2026 direct image of glowing hydrogen along cosmic web filaments at redshifts of 9 to 11 billion light-years ago confirms what simulations have predicted for decades. The structure of the universe is a web. The web is mostly holes. The threads contain the galaxies. The holes contain almost nothing at all. Take all of this in. The largest structures in the universe, at every scale we can survey, from megaparsecs to gigaparsecs, are voids. Filaments contain over 50% of the matter in the universe, but only a small fraction of the volume. The rest of the volume is empty. Not empty of stars, although it is largely empty of those. Empty of substance, full stop. A typical hydrogen atom in intergalactic space is separated from its nearest neighbor by about 1 meter. There is more atomic density inside a single cubic centimeter of your eyeball than there is in a cubic kilometer of intergalactic space. This is the third scale of cosmic emptiness. The first was the atom. The second was the solar system and the galaxy. The third is the cosmic web, the largest visible structure in the known universe. At every scale, the void is the rule. The atoms inside you, the orbit around the sun, the disk of the Milky Way, the structure of the cosmos itself, all of it, mostly nothing. I want to slow down for one paragraph, because there is a secondary kind of emptiness that we have not named yet, and it deserves a moment of attention, even though we are not going to dwell on it tonight. The universe, as far as we can hear, is also empty of company. The Fermi paradox, the simple, unsettling question of why, if life is common, we have never heard from anyone else, has hovered over astronomy since the 1950s. The sky is large. The sky has been large for billions of years. The sky should be full of signals. The sky is quiet. We are not going to walk that road tonight. It is its own video, and a long one. But notice the resonance. The emptiness of the cosmos has another layer, not just empty of stuff, but empty of voices. The structure is silent. Whether that silence means anything is a question I will gently leave with you, but I wanted you to feel it. And there is one more thing. We have been saying, throughout this part, that the visible matter accounts for only 5% of the universe. We have not yet said what the other 95% is. That is where we are going next. Because once you discover that 95% of the universe is invisible, the question stops being, is the universe empty? And starts being, is the universe even made of what we think it is at all? Let me show you the inventory. And then I want to take you inside the empty space itself, because I promise you, the emptiness has a story of its own. A story that is, in some ways, even more strange than the one we have already heard. Is less than break time equals 1s. Is greater than number part 7, the dark sector. So far tonight, we have been talking about emptiness as the absence of matter. We have toured the spaces between atoms, between planets, between stars, between galaxies. We have established that almost all of the volume of the universe is, by any honest accounting, vacant. Now I want to do something that, depending on how you look at it, makes the picture either better or worse. I want to look at what fills the volume. The cosmic inventory, in round numbers, goes like this. About 5% of the total mass energy of the universe is ordinary matter atoms, the stuff you and I and the chair and the floor and the planet and the sun and the visible stars are made of. About 27% of the universe is dark matter, something that has mass and gravitates but does not interact with light. About 68% of the universe is dark energy, something with negative pressure that drives the expansion of space and behaves, to the best of our current measurements, like an intrinsic property of the vacuum itself. 5, 27, 68. Add them up, around 100%. Ordinary matter is the smallest slice. 95% of the universe is invisible. Now let me take that 5% and zoom in. Of the ordinary matter, most is not in stars. Most is not in planets. Most is, in fact, hot, thin, diffuse gas drifting between galaxies, what astronomers call the warm hot intergalactic medium, or the intracluster medium. The stuff that is actually in stars and planets and people and chairs is a small fraction of the 5%. Conservative estimates put the fraction of the universe that exists in any solid, condensed, recognizable form at less than 1/10 of 1%. By volume, the fraction is even smaller. By volume, the universe is, to a precision I find difficult to overstate, almost nothing. Dark matter is the more familiar of the two unknowns. We know it exists because we can see its effects. The rotation curves of galaxies, the speeds at which stars orbit the galactic center, do not match the speeds we would predict from the visible mass alone. Galaxies are spinning too fast for their visible matter to hold them together. They should fly apart. They do not fly apart. Something else is gravitating, and that something else is, in most galaxies, about 5 times the mass of the ordinary matter. We see dark matter's effects in gravitational lensing, the way the light from distant galaxies is bent as it passes mass concentrations in front of us. We see it in the cosmic microwave background. The leftover radiation from the early universe contains acoustic features that match the predictions of a universe with significant dark matter and do not match the predictions of a universe without it. We see it in the formation of large-scale structure. The cosmic web simply could not have grown to the size and complexity it has in the time available, starting from the tiny density variations we see in the cosmic microwave background, without a large reservoir of dark matter to draw the ordinary matter into wells. What dark matter actually is, we do not know. 20 years ago, the leading candidate was a class of particles called weakly interacting massive particles, or WIMPs. Direct detection experiments, large tanks of liquid xenon buried under mountains to shield them from cosmic rays, have been looking for WIMPs for decades. They have not found them. The leading candidate today is a particle called the axion, theoretically motivated for other reasons, and recently the focus of intense experimental effort. Primordial black holes have a niche following. A small minority of physicists prefer modifications of gravity, the Mond framework, over a particle explanation. The question remains open. What is not open is the fact that something is there. The mass exists. The gravitational effects are real. The cosmic web maps from JWST and from earlier surveys reveal a scaffolding that traces dark matter, with galaxies sprinkled on top like foam on a wave. The structure of the universe is, in a profound sense, a structure made of an unseen thing. We live inside scaffolding that we cannot touch. Dark energy is even stranger. It does not seem to be a particle at all. It does not seem to clump. It does not seem to flow. It behaves, in all the measurements we have done, like a constant pressure built into the geometry of space itself, a property of the vacuum that pushes empty space apart at a rate proportional to how much empty space there is. The more vacuum exists, the more dark energy exists, the more the vacuum expands. The result is the accelerating expansion of the universe, confirmed in 1998 by the Type Ia supernova surveys of Rees, Perlmutter, and Schmidt, which earned them the Nobel Prize in 2011. I want you to notice the implication. Most of the universe is something that lives in empty space rather than something that occupies it. The volumes between galaxies are not just empty of stuff. They are full of dark energy, a force that pushes them outward, expanding them, making them emptier with each passing second. The largest single component of the cosmos is something that does not fit our intuitive category of stuff at all. It is a property of nothing. This is where the central thread starts to wobble in a productive way. We have been saying all night that the universe is mostly empty, but empty is starting to do double duty. There is empty in the sense of no atoms here, which is true of nearly all volumes, and there is empty in the sense of nothing happening here, which turns out not to be true at all. The dark sector is everywhere. The dark sector fills the volume. Most of the universe is invisible to light, but visible to gravity. Most of the universe is doing something quietly, persistently, on the largest scales, even where we cannot see it. Where this leads, in the next part of our walk, is one of the strangest revelations in modern physics. It turns out that even the part of empty space that we thought was empty, the bare vacuum of quantum field theory, the floor of physical reality, is not empty either. It is so full of activity that when we try to calculate how much energy it should contain, we get the most embarrassingly wrong answer in the history of science, by a factor of 10 to the 120th. The vacuum is hiding something. The hiding place is everywhere. So let's go in. Let's look at the emptiness from the inside, and let's find out why some physicists describe the quantum vacuum as the loudest place in the universe. Is less than break time equals 1s, is greater than. Number, part 8. The quantum vacuum is loud. When physicists try to describe what is left, after you remove everything from a region of space, every atom, every photon, every particle of any kind, even the cosmic microwave background, they end up with something called the quantum vacuum. The name is a little misleading. In quantum field theory, the vacuum is not the absence of stuff. It is the lowest possible energy configuration of all the fields that fill space. Every fundamental field, the electron field, the photon field, the quark fields, the Higgs field, the gluon field, all of them has its own ground state. Together, those ground states define what we mean by empty. Now here is the strange part. The ground state is not zero. The energy of an empty region of space, according to quantum mechanics, is not zero. It cannot be zero. The reason it cannot be zero is the Heisenberg uncertainty principle. You may remember the uncertainty principle from part 2, the rule that says you cannot know a particle's position and momentum simultaneously to arbitrary precision. The same principle applies to fields. You cannot specify, simultaneously and exactly, both the value of a field at a point and the rate at which that value is changing. The product of those uncertainties has to be at least Planck's constant divided by 2, which means that no field can ever be exactly zero everywhere. There is always some residual jitter, some fluctuation, at every point in space, in every field, at all times. The jitter has a name. It is called zero-point energy. It is the lowest possible energy a quantum system can have, and it is not zero. This may sound like an abstraction, but it has consequences you can measure. The jitter in the electron field, for example, manifests as what physicists call virtual particles. Pairs of electrons and positrons popping briefly into existence and annihilating again, allowed by the uncertainty principle to borrow energy from the vacuum as long as they return it within a short enough time. Pairs of photons, pairs of quarks, pairs of everything, every field, at every point in space, all the time, bubbling. The vacuum is the most active region in the universe. We just cannot normally see the activity because the borrowed energy is returned before it can be observed. But we can see the consequences. The most famous example is the Casimir effect, predicted in 1948 by the Dutch physicist Hendrik Casimir. Here is how it works. Imagine two metal plates, electrically neutral, placed very close together within a few micrometers of each other in a perfect vacuum. According to classical physics, there should be no force between them. According to quantum field theory, there is. The reason is subtle. Outside the plates, virtual photons of all wavelengths can pop in and out of existence. Between the plates, only virtual photons whose wavelengths fit neatly between the two surfaces can exist. The plates restrict the possibilities. The result is that the energy density of the vacuum between the plates is slightly lower than the energy density outside them. Lower energy density means lower pressure. The plates are pushed together by the imbalance. The effect has been measured in the laboratory many times with high precision. It is real. Let me restate that, because the implication is enormous. The Casimir effect proves that the empty space between two plates is doing something. It has an energy density. It can be perturbed. The perturbation produces a force. The vacuum is not a passive stage on which physics happens. It is an active participant. The emptiness pushes. There is another, older, quieter piece of evidence. In 1947, Willis Lamb, working at Columbia University, measured a tiny shift in the energy levels of hydrogen, what is now called the Lamb shift. The shift is caused by the electron in the hydrogen atom interacting with virtual photons in the vacuum surrounding it. The vacuum tugs on the electron. The tug shows up as a measurable change in the hydrogen spectrum. Lamb won the Nobel Prize in 1955 for the discovery. The first hard experimental confirmation that empty space has effects on the matter inside it. The vacuum, even when it appears to be empty, is doing work. There is a third piece of evidence that I want to mention because it is so beautifully concrete. In 2011, a team at Chalmers University of Technology in Sweden, led by the physicist Christopher Wilson, performed an experiment called the dynamical Casimir effect. They built a superconducting circuit and rapidly varied its boundary conditions, effectively shaking the vacuum very fast. The result was the production of real, measurable photons, light generated out of nothing by perturbing the geometry that bounded the vacuum. The photons were not borrowed from somewhere else. They were brought into the world by the act of disturbing the field. The experiment was a direct demonstration that the quantum vacuum, when shaken, will give up some of its energy as actual particles. This is, in a very literal sense, conjuring something from nothing. And it works. We have done it in the laboratory. I want to pause on what these three pieces of evidence, the static Casimir effect, the Lamb shift, and the dynamical Casimir effect together, establish. They establish that the vacuum is a real physical thing, not a backdrop, not a stage. A physical system with its own structure, its own energy, its own susceptibility to perturbation. You can measure it, you can perturb it, you can extract photons from it under the right conditions. The vacuum is not the absence of physics. The vacuum is the bottom of physics. It is the field at its lowest setting, and the lowest setting is still humming, and then we get to the problem. When physicists calculate, from quantum field theory, how much energy the vacuum should contain, they get an enormous number. The calculation sums the zero-point energies of every mode of every field at every point in space, up to some cut-off scale. The cut-off is typically taken to be the Planck scale, the scale at which our current theories break down. The result is an energy density of about 10 to the 113th joules per cubic meter. That is an unfathomable amount of energy per cubic meter. Then we look at the sky. We measure the rate at which the universe is expanding. We measure the rate at which the expansion is accelerating. We use those measurements to calculate the actual energy density of the vacuum, the so-called cosmological constant. We get a number that is much, much, much smaller, around 10 to the negative 9th joules per cubic meter, vanishingly small, almost zero, but not quite. The ratio between the theoretical prediction and the observed value is about 10 to the 120th, a 1 followed by 120 zeros. The theoretical prediction is off by a factor that is, quite literally, larger than every other number we can usually write down in physics. It is the largest discrepancy between theory and observation in the history of science. Physicists call it the cosmological constant problem. Some physicists, more pointedly, call it the worst prediction in the history of physics. What does the discrepancy mean? We do not know for sure, but one consequence of it is undeniable. Either we are doing the calculation wrong, in some way no one has yet figured out, or the universe has been fine-tuned to a value of vacuum energy that is staggeringly precise. The dial that sets the energy of empty space has been set to a value that is, against all theoretical expectation, vanishingly close to zero, slightly off zero, but only slightly. If the dial had been set even a tiny bit higher, the universe would have expanded so fast that no galaxies could form, no stars could ignite, no life could arise. If the dial had been set negative, the universe would have collapsed long before life could appear. The dial sits at exactly the value required for us to be here. We do not know why. There are several proposed answers. One, the multiverse, or anthropic, answer says that many universes exist with many different values of the vacuum energy, and we observe a small one because larger ones would not permit observers. This is, in many ways, an admission rather than an explanation. We exist where we can. The other universes are out of reach, but they have to exist for the answer to work. Another answer, supersymmetry, proposed that for every known particle, there should be a supersymmetric partner whose contribution to the vacuum energy would cancel the known particle's contribution. The Large Hadron Collider has not, so far, found the supersymmetric partners. Other answers, modified gravity, quintessence fields, novel symmetries, are all on the table, none yet convincing. I want to give you a sense of how strange the multiverse answer feels from the inside. When physicists talk about a multiverse in this context, they do not typically mean a sci-fi multiverse of alternate Earths and parallel histories. They mean something more architectural. They mean a structure in which the laws of physics, or the values of fundamental constants, can vary from region to region. In some inflationary models, the early universe gave rise to an enormous number of pocket universes, each born from a slightly different fluctuation of the inflaton field, each settling into a slightly different vacuum configuration. The string theory configuration space, a kind of map of possible stable vacua, is sometimes cited as having around 10 to the 500 distinct possibilities. If even a small fraction of those possibilities ever existed, then somewhere in the larger structure, the cosmological constant is the precise tiny value we observe. We are the universe that worked out. The others either expanded too fast for galaxies to form, or recollapsed too quickly for anything to evolve, or settled into a configuration where chemistry did not exist at all. The anthropic answer says, in effect, that we should not be surprised to find ourselves in the one that worked. We could not be anywhere else. The horror, in this framing, is not that the universe is fine-tuned. The horror is that the fine-tuning may be a selection effect, and almost everywhere else, in the larger architecture, the experiment failed. A few physicists find this kind of explanation unsatisfying as a matter of principle. It explains the value of the constant by appealing to an unobservable structure outside our universe, which can feel like a card that cannot be checked. Others find it the only sensible answer, given how precisely tuned our value appears to be. The debate has not converged. It may not converge for a long time. What is not in doubt is the number itself. 10 to the negative 120th, the most precise, unexplained quantity in the equations of physics. Sitting calmly at the center of every cubic centimeter of empty space in the cosmos, holding the structure of the universe in shape by being exactly what it is, and not even slightly more, what is undeniable is the precision. The emptiness of the universe is not just present, it is calibrated to a level of accuracy that, from inside our current theories, looks like an extraordinary coincidence. Either the universe is fine-tuned for our existence by some mechanism we have not understood, or the universe is one outcome among many in a much larger structure that we cannot observe. Either way, the design language earns its place. Whether the designer is mathematical, multiversal, or simply unknown, the result is the same. The emptiness has been set to a precise value. Move it, and we vanish. I want to take a moment, before we move on, to step into stranger territory, fringe but real, as I like to think of it. The fact that the quantum vacuum has energy has, for a long time, attracted the attention of inventors looking for free energy. Zero-point energy as a power source. Devices to extract usable work from the vacuum. Most physicists say, calmly and persistently, that this is forbidden by conservation of energy. You cannot remove energy from the vacuum and end up with less of it, because the vacuum is, by definition, the lowest energy state. There is nowhere for the energy to go. Patent offices around the world reject zero-point energy, perpetual motion claims as a matter of policy. The Casimir effect can produce real forces, but the forces do not extract net energy from the vacuum on the whole. The energy comes from the configuration, not from the vacuum itself. We mention this here as cultural color, not as physics. The vacuum has energy. The energy is not yours. There is one more idea I want to plant, because we will come back to it in part 11. The Higgs boson, discovered at the Large Hadron Collider in 2012 at a mass of 125 giga-electron volts, places our universe in what physicists call a metastable vacuum. The Higgs field has settled into a configuration that is stable enough to last a very long time, but it may not be the absolute lowest possible energy. There may be another, deeper minimum somewhere else in the field, separated from ours by a barrier that, in principle, quantum tunneling could cross. If it ever did, if a bubble of true vacuum nucleated anywhere in the observable universe, that bubble would expand at the speed of light and rewrite the local laws of physics inside the bubble wall. Chemistry as we know it would, very likely, not be possible inside. The peer-reviewed phrase for our condition is metastable, but extremely long-lived. We will revisit this in our final tour of the future. For now, the takeaway is that even the emptiness we have is not necessarily the most stable one available. The vacuum has at least one more story to tell, possibly a less hospitable one. Now, I want to bring this back to the central thread, because we have just done a lot of work and the picture is shifting in an important way. Across every void we have toured tonight, the void inside the atom, the void between the planets, the void between the stars, the void between the galaxies, the void inside the great Boötes and Eridanus and KBC superstructures. That void is full of this, full of quantum fluctuations, full of virtual particles, full of zero-point energy, full of dark energy, full of all the things that are not stuff but are present anyway. The voids are not absences. They are the architecture of the universe expressed in its purest form. They are the canvas, fine-tuned to a value we cannot yet derive, on which a few specks of matter have briefly arranged themselves into something complex enough to ask questions. The emptiness, in other words, is not empty. It is precisely tuned. And what makes the universe horrifying, if it is horrifying, is not that there is so little stuff in it, It is that even the nothing has a designed value. The hollow is precise. The hollow has rules, which raises a question I have been holding back. If even the bare vacuum is not empty, if even the absences are full of structure, is it possible that the universe we know is even more empty than the picture has so far suggested? That what we call substance is itself a kind of trick? That the visible matter is even more of a rounding error than 5% of total mass energy, and the universe is fundamentally a hollow even at the layer beneath our hands? Let's take a short detour. I want to mention, briefly, one of the strangest and most respectable ideas in modern theoretical physics, because it would change the picture in a way that, if true, is worth your evening having heard. Is less than break time equals 1s is greater than number, part 9, a brief detour through a hologram. In the 1970s, the physicist Jacob Bekenstein noticed something peculiar about black holes. When matter falls into a black hole, the black hole's surface area increases in a way that turns out to track the entropy, the amount of information that the matter contained. The amount of information that can fit inside a black hole, in other words, is proportional to the area of its surface, not its volume. This was deeply strange. Information, intuitively, should scale with volume, the way bytes scale with the size of a hard drive. The surface area scaling suggested that information about the interior of the black hole was somehow encoded on its boundary. A decade later, working from this and other clues, the theorists Gerard Hooft and Leonard Susskind generalized the idea into what is now called the holographic principle. The principle states that all the information needed to describe what is happening inside a region of space can be encoded on the two-dimensional surface that bounds the region. The interior of any volume, in this sense, is redundant with its boundary. The third dimension may, at some level of description, be a kind of projection, a hologram. The holographic principle has since been confirmed in a precise mathematical sense for certain idealized models, the so-called ADS, CFT correspondence, pioneered by Juan Maldacena in 1997, which links a theory of gravity in five-dimensional anti-de Sitter space to a quantum field theory living on its four-dimensional boundary. Whether the principle applies to our universe, in our actual geometry, is unproven, but many physicists take it seriously as a candidate principle of the most fundamental layer of reality. If the holographic principle is correct for our universe, the implications for our story tonight are remarkable. The interior of every void, every space between atoms, every gap between stars, every cosmic void hundreds of millions of light years across would, in some profound sense, not actually contain what we think it contains. The information defining the interior would live on a far distant surface. The bulk of space would be even emptier than it appears, because it would not even be the seat of its own contents. The substance of reality, in this view, may not occupy the volumes we walk through at all. Reality may live on a screen we cannot reach. This is speculative, and I am not asking you to believe it. I am asking you to hold it as one possible reading of the picture we have been building, because if it is true, the central thread of our walk tonight becomes even sharper. The universe is not just structurally empty in the ordinary sense, empty of atoms, empty of stuff. It may also be empty in a more radical sense. The volumes of three-dimensional space may not contain anything in their own right. They may be a projection. The body of reality may be a surface, and the interior may be a stage set. The hollow we have been describing may be even more profoundly hollow than the standard inventory suggests. I will leave the detour there, because the road back to safer ground is the one I want to take next. Whatever the deepest principle of physics turns out to be holographic, multiversal, or something we have not yet imagined, the dark energy we discussed in Part 7 is doing something measurable to the universe right now. It is pulling the emptiness apart. and it is doing so at an accelerating rate. The receding sky is the next thing we look at. Because once you understand what dark energy is doing in real time, you understand why the final part of our tour, the part where we look at the future of the cosmos, lands on the word horrifying, is less than break time equals 1s, is greater than number, part 10. Dark energy and the receding sky. Until 1998, most cosmologists believed that the expansion of the universe was slowing down. The reasoning was simple. The Big Bang had imparted a kinetic energy to all the matter in the universe, pushing it outward. The gravitational attraction of that matter, pulling everything back toward everything else, should be slowing the expansion. The question of cosmology was, how much was it slowing, and would the deceleration ever become a halt, and after that a contraction, ending in a big crunch? In 1998, two teams, one led by Saul Perlmutter at Berkeley, the other co-led by Adam Rees and Brian Schmidt at Harvard and the Australian National University, published independent results based on observations of type Ia supernovae in distant galaxies. Type EAE supernovae are useful because their intrinsic brightness is highly consistent. They are standard candles. If you know how bright they should be, you can use how bright they appear to calculate how far away they are. And from how far away they are, combined with their redshift, you can work out the history of the expansion. Both teams found something they did not expect. The supernovae were dimmer than they should have been if the expansion was decelerating. They were dimmer than they should have been, even if the expansion was constant. The only model that fit the data was a universe in which the expansion was accelerating, not slowing, not steady, speeding up. This was, at the time, one of the most surprising results in the history of cosmology. It implied the existence of something soon named dark energy that was acting as a kind of anti-gravity on the largest scales, pushing space apart, and doing so more strongly the more space there was. The discovery earned the three lead investigators the Nobel Prize in 2011. It is now confirmed by independent measurements from the cosmic microwave background, from baryon acoustic oscillations, from large-scale galaxy surveys, and most recently from the Dark Energy Spectroscopic Instrument DESI at Kitt Peak in Arizona. DESI completed its planned three-dimensional map of the universe in April of 2026. The map contains spectroscopic redshifts of more than 40 million galaxies and quasars, spanning 11 billion years of cosmic history. It is the most precise, large-scale map of cosmic geometry ever made. Combined with the Pantheon Plus supernova catalogue and the Planck cosmic microwave background data, DESI's second data release this year provided a slightly disconcerting hint. The data are mildly inconsistent with a simple cosmological constant, a dark energy whose strength stays the same forever. The data prefer, by roughly 2.8 sigma to 4.2 sigma, depending on which supernova sample is used, a dark energy that evolves with time. Specifically, a dark energy that was slightly stronger in the past and is becoming slightly weaker as the universe ages. The signal is suggestive, not conclusive. A consistency check published in May of this year raises systematic error concerns that may eventually account for the apparent evolution. The science is, in the literal present tense, unsettled. But notice what is at stake. If dark energy is constant, the future of the universe is one kind of empty. If dark energy is evolving, getting stronger over time, the future is much, much more empty. There is a scenario called the Big Rip, in which dark energy grows so dominant that, in some finite time, it overwhelms the gravity holding galaxies together. Then it overwhelms the gravity holding solar systems together, then planets, then molecules, then atoms, then nuclei. The fabric of space is pulled apart, faster than light can cross it, and everything is shredded into the smallest possible pieces. If dark energy is evolving in the opposite direction, getting weaker, the future is more sedate. The expansion still accelerates, but less dramatically, and the universe coasts toward a long, slow heat death rather than a rip. Either way, the future is empty. The only question is whether the emptiness arrives violently or quietly. The current data favor a quiet ending, with a possible mild evolution that, by DESI's measurements so far, is more consistent with a softening dark energy than a strengthening one. Most physicists, looking at the current evidence, would still bet on heat death, but the universe is reserving the right to surprise us. Let me put the consequences of accelerating expansion into concrete terms, because they are sometimes lost in the math. Right now, in 2026, we can see, with telescopes, galaxies whose light has been traveling toward us for more than 13 billion years. The most distant galaxies we have ever identified, found by the James Webb Space Telescope, formed when the universe was only a few 100 million years old. The observable universe, the volume of space whose light has had time to reach us since the Big Bang, is roughly 93 billion light-years in diameter, because the space itself has expanded while the light was in transit. But not all of those distant galaxies will always be visible to us. Some of them, the most distant, are already receding from us faster than light. We can still see them, because the light that left them billions of years ago is still in transit and still reaching us. But the galaxies themselves are no longer reachable, and their future light, emitted today or tomorrow, will never get here. They have crossed our cosmological horizon. They are gone not because they vanished, but because the space between us and them has stretched faster than light can cross it. As the expansion continues to accelerate, more and more galaxies will cross our horizon. The volume from which light can ever reach us will shrink. Not in absolute size, the volume in our own coordinates stays the same, but in content. The galaxies inside it will be redshifted out of detectability, one by one, and then they will simply be unreachable. Roughly 150 billion years from now, about 10 times the current age of the universe, almost everything outside our local group will have receded beyond view. The local group consists of the Milky Way, Andromeda, the Triangulum Galaxy, and several dozen dwarf galaxies, all bound together by mutual gravity. The local group is gravitationally stable against dark energy at its current strength. So the local group will hold together while everything else recedes. By that time, the Milky Way and Andromeda will have already merged into a single elliptical galaxy. Future astronomers, looking out from a planet around some red dwarf in that merged galaxy, will see their own galaxy and otherwise nothing, no other galaxies. The cosmic microwave background will have stretched into wavelengths so long they cannot be detected. The Hubble diagram, the evidence of expansion, will have become invisible. The future astronomers, in other words, will be staring at the sky we would have seen if the Milky Way had formed inside the Boat's void in the first place. The history of cosmology will be unprovable. The expansion will be over, for them, as a piece of observable science. The universe will simply appear to be one galaxy in a sea of black. And there is one more piece of news worth mentioning before we move on. As I mentioned in Part 6, the KBC void, the possible 2 billion light-year underdensity in which we may sit, could distort our local measurements of the expansion rate. The Hubble tension, the disagreement between local and cosmic microwave background measurements of the Hubble constant, may be partly an artifact of where we live in the cosmic emptiness. The current tension stands at about 5 sigma statistically significant, hard to dismiss. If part of it is geometric, then the picture of accelerating expansion may need adjustment. If none of it is geometric, we may need new physics. The puzzle has been deepening for nearly a decade. The next year of data, Euclid's first major cosmology release, is scheduled for October of this year, 2026 may, finally, start to give us answers. Let me bring this back to the thread. We are now adding time to the picture of cosmic emptiness. Until now, we have been describing how empty the universe is right now. But the universe is not static. The emptiness is growing. Every second, more cosmic real estate becomes void. Every second, the visible universe shrinks. The dark energy is winning. The architecture is, in the language of equations, asymptotically empty. The destination, in the current best models, is heat death, a state of maximum entropy in which nothing useful happens anymore, anywhere, ever again. That is where we go next, the far future. The architecture of cosmic emptiness, projected forward in time, until time itself runs out of things to do. Take a breath. This is the part that earns the word in the title. Is less than break time equals 1s. Is greater than number part 11. Everything ends empty. Physicists divide the future of the universe into 4 enormous eras. The names are descriptive. Each one ends when a particular kind of structure has run its course. The total span, from the beginning to the asymptotic end, is something on the order of 10 to the 100 years, an interval so long that the current age of the universe is, by comparison, the blink of an eye in a lifetime of immeasurable length. We are currently in the stelliferous era, the age of stars. It began about 100 million years after the Big Bang, when the first stars ignited. We are about 14 billion years into it. It is a brief, brilliant moment by the standards of what comes next. The stelliferous era will end in roughly 100 trillion years, when the last red dwarf, the longest-lived of all stars, burns through its hydrogen and contracts into a white dwarf. After that, no new stars will form. The fuel will be gone. The skies will go dim, slowly, over hundreds of trillions of years, as the existing stars fade and no new ones replace them. After the stelliferous era comes the degenerate era. The cosmos will be populated by white dwarfs cooling toward absolute zero, neutron stars cooling toward absolute zero, brown dwarfs that never quite ignited, and the occasional black hole. Stellar collisions become rare because the population is thin and the volumes are enormous. In one of the more remarkable predictions of the Standard Model, if the proton is unstable, if it can decay, even on extraordinarily long timescales, then ordinary matter itself will dissolve. Protons may have a half-life as long as 10 to the 34th years or more. Over enough time, every proton in every white dwarf, in every neutron star, in every piece of ordinary matter in the universe, will decay into lighter particles. The white dwarfs will evaporate, the neutron stars will evaporate. By about 10 to the 40th years, if proton decay is real, the universe will contain no ordinary matter at all. Some physicists doubt proton decay. The current best experimental lower bound on the proton's lifetime is around 10 to the 34th years extraordinary, but consistent with there being no decay at all. If protons are perfectly stable, the white dwarfs and neutron stars persist much longer, and the degenerate era stretches to something like 10 to the 65th years before quantum tunneling slowly converts the cold stellar remnants into iron stars and then into black holes. Either way, by some unimaginably distant time, ordinary matter is gone, and the cosmos is populated entirely by black holes. This brings us to the black hole era. Black holes are not eternal. They radiate very slowly through a quantum process discovered by Stephen Hawking in 1974, Hawking radiation. The radiation is faint for a black hole. The mass of the Sun, the radiation is so weak that the black hole loses essentially no mass over the current age of the universe, but it never stops. Over time, spans of 10 to the 67th years, even a stellar mass black hole will radiate away its mass and disappear in a final burst of energy. Larger black holes, take longer. The supermassive black holes at the centers of galaxies, the largest with masses of tens of billions of times the mass of the Sun, take on the order of 10 to the 100th years to fully evaporate. After they evaporate, the cosmos is left with nothing but a very thin, very cold gas of photons and stray particles, drifting through enormous volumes of space, with no structure, no gradients, no useful sources of energy. The Dark Era. By about 10 to the 100th years, the universe is asymptotically empty. No stars, no planets, no galaxies, no black holes, no useful structure of any kind. Just a faint, cold, expanding fog. The temperature in the Dark Era approaches absolute zero, but never quite reaches it. There is always some residual quantum activity, some leftover radiation, but the universe, by any useful measure, has stopped producing anything new. The story is over. The room has emptied. The lights have all gone out. Now I want to sit with that picture for a moment, because it is important to feel it. We have spent the night describing how empty the universe is right now. That emptiness is, by the math, a transient state. It is going to get worse, much worse. Every star that currently burns will eventually burn out. Every planet that currently orbits will eventually be lost either to the death of its star, or to gravitational ejection, or to proton decay, or simply to the slow cooling that follows the last of the available energy gradients being smoothed away. There will not be a single warm place anywhere in the cosmos, no matter where you look, for an interval longer than the current age of the universe times every number we have ever written down combined. That is heat death. It is not a sudden ending. It is a fade. The room empties slowly, patiently, with the most unhurried thermodynamics imaginable. There is a wrinkle in this picture that I want to talk about because it is genuinely strange. The wrinkle is called the Boltzmann brain problem. In a universe that has reached heat death, that has settled into a de Sitter equilibrium with a tiny but non-zero temperature, expanding forever quantum fluctuations should occasionally produce structured matter. The probability of any particular fluctuation is very low, but the timescale is, by stipulation, infinite. Over infinite time, even very improbable events should happen. And among the things that should occasionally fluctuate into existence, statistically, are brains. Brains complete with memories and experiences. Brief, isolated structures that, for a few moments, possess the configuration we call consciousness. The math works out, on standard assumptions, in a peculiar way. In a universe that lasts forever, the number of brains that arise from biological evolution is finite. There are only so many generations of stars, so many planets, so many evolutionary pathways. But the number of brains that arise from random vacuum fluctuations is potentially unlimited because the timescale on which they can fluctuate is unlimited. So if you ask what is the most likely origin of an observer in this universe, by sheer combinatorics, the answer may be a Boltzmann brain, fluctuating into existence in the heat-death era with false memories of a coherent life. You can see where this is uncomfortable. If Boltzmann brains vastly outnumber ordinary observers, then by self-consistency you should expect that you are most likely to be a Boltzmann brain, your memories are most likely false, and the apparent coherence of your experience is most likely about to dissolve. Physicists treat this seriously enough that it functions as a constraint on cosmological models. A model that predicts more Boltzmann brains than ordinary humans is widely considered to have made a mistake somewhere. We refer to this as the Boltzmann brain problem. The mainstream resolution is some combination of maybe the universe will not last long enough to produce Boltzmann brains. Maybe the relevant kind of fluctuation does not actually produce coherent observers. Maybe the multiverse is structured in a way that selects against them. The resolutions are unsatisfying. the problem persists. I do not want to dwell on this, because I do not believe, and most physicists do not believe, that you are actually a Boltzmann brain. But I do want to acknowledge that the asymptotic emptiness of the cosmos has implications for what kinds of consciousness can arise within it. And those implications are, when you sit with them quietly in the late evening, slightly horrifying. The far future of the cosmos may contain more disembodied flickers of mind, each believing itself to be a person, than it ever contained actual persons. Most of the experience in the history of the universe may turn out to be lonely, brief, mistaken. We may be among the small set of conscious observers fortunate enough to have arisen during the warm, stelliferous interval rather than the cold, dark era. The fortune of being early, the fortune of being warm. We do not always think to be grateful for those. Let me linger on one more disquieting feature of the projected end state before we look for any reprieve. In the dark era, when the cosmos has reached its asymptotic quiet, the volumes involved become so enormous that ordinary intuition fails completely. A photon, emitted near one end of the cosmos and headed toward the other end will, in a typical case, travel for a stretch of time that exceeds the current age of the universe by a factor so large that no notation we have ever invented can comfortably hold it. The photon will arrive somewhere, eventually. There will be no one there to greet it. There will be no one anywhere, in fact, to greet anything. The cosmos becomes a structure inside which arrival has stopped meaning much. There will still be space. There will still, technically, be time. There will simply be nothing happening inside either of them. Some physicists describe this end state as a kind of solitude. They mean it as a technical term. In the dark era, every particle is, on average, so far from every other particle that interactions become vanishingly rare. The few interactions that do occur take place across distances that, by our current standards, beg a belief. Each particle is, for all practical purposes, alone. The structure of cosmic emptiness has been refined by the slow work of expansion into individual loneliness. The atom was empty, the galaxy was empty, the void was empty. The endpoint is each particle empty of every other. There is a possible reprieve, and I want to mention it because the picture is too bleak without it. The physicist Roger Penrose has proposed a cosmological model called conformal cyclic cosmology, in which the asymptotic empty future of one universe rescales through a mathematical equivalence into the hot dense beginning of the next. The argument is subtle. In a universe in which all massive particles have decayed and the only remaining content is radiation, there is no clock and no scale. Infinitely large and cold is mathematically indistinguishable from infinitely small and hot. The end of one cosmological cycle may, under the right interpretation, be the Big Bang of the next. Penrose has even claimed to have found possible imprints of the previous cycle in the cosmic microwave background, in the form of concentric rings, though these claims are contested and not generally accepted. A related idea, the Steinhardt-Turok ekpyrotic model, proposes that our universe is one in a long succession of cycles produced by the collision of branes in a higher dimensional space. In every cycle, expansion eventually exhausts itself. The cycle ends in an empty de Sitter state, and the collision with another brane initiates a new Big Bang. The empty heat death is, in this picture, the seed of the next universe. There is a further version of cyclic cosmology, sometimes called the bouncing universe, in which our Big Bang is not a true beginning, but a bounce, a contraction of a previous universe, which became too dense to keep contracting and rebounded into expansion. In some bouncing models, the previous universe was a mirror image of ours, with arrows of time and entropy that ran in the opposite direction. The bounce is the point at which time flips. In other bouncing models, each cycle slightly differs from the last, and the cosmos slowly evolves through a great chain of universes, each one a small variation on its predecessor. The mathematical machinery for these ideas is precise. The empirical evidence is sparse. Most cosmologists treat them as interesting possibilities rather than as established physics. But they do offer one quietly remarkable thing, a picture in which the emptiness we are heading toward is not a terminus, it is a stage. The story does not end, it transforms. The empty room is not the last room, it is the antechamber to the next room. I want to be careful here, because I do not want to oversell a reprieve that the math does not quite buy us. Even in the most successful cyclic models, the universe we know, the one our atoms, our planet, our species occupy still ends. The cycle that includes us has a final paragraph. A new cycle begins somewhere else, in some sense after, but the warmth we have now does not survive into it. The continuity, if there is continuity, is mathematical rather than personal. The next universe inherits the geometry, not the inhabitants. So the cyclic picture is, at best, a kind of cosmic relay race in which our team finishes its leg and hands a structureless baton to a team we will never meet. There is a beauty in that. There is also, if you sit with it, a quiet melancholy. The story continues. We do not. That is true even with the most generous reading of the most optimistic models. We mention these gently. They are speculative. They are not the mainstream view, but they offer a tiny note of optimism in an otherwise bleak forward projection. The emptiness, in cyclic cosmologies, may not be the last room. It may be a doorway. And there is one more thing that I promised to come back to in Part 8. The vacuum we live in may not be the deepest possible vacuum. The Higgs boson, measured at 125 giga-electron volts, places the standard model vacuum in a metastable regime. There is a possibility, small, but not zero, that the vacuum could decay, that a bubble of true vacuum could nucleate anywhere in the universe, at any time, by quantum tunneling. The bubble would expand at the speed of light. Inside it, the laws of physics would shift. Chemistry as we know it would, very likely, not be possible. We would not see it coming. The closest we would get to warning is the moment the bubble wall crossed our world line. The peer-reviewed literature describes our vacuum as metastable but extremely long-lived. Estimated lifetime is well past 10 to the 100th years. This is, in practical terms, not a worry. In theoretical terms, it is one more reminder that even the emptiness we have, the vacuum that lets atoms form and stars burn and brains experience things, is not necessarily the lowest possible emptiness. There may be a deeper hollow, there may be a more thorough nothing. The universe has not finished telling us how empty it can be. Let me now reconnect to the central thread, because we have just toured a great deal of asymptotic darkness, and the thread is the thing that keeps it from being merely depressing. Emptiness inside atoms, enforced by quantum law. Emptiness between planets, enforced by gravitational geometry. Emptiness inside galaxies, enforced by the local clumping of matter. Emptiness between galaxies, enforced by the structure of the cosmic web. Emptiness in the dark sector, where the bulk of the mass energy of the universe lives outside our ability to see it. Emptiness in the quantum vacuum, finely tuned to a value we cannot derive. Emptiness in the future, growing without limit. Every layer of the universe we have visited tonight has been structured around nothing, and the structure is converging on a single end state of asymptotic emptiness. The horror, if there is one, lives here. The emptiness is winning. It has been winning since the first second after the Big Bang. We have been living, briefly, inside its hesitation. And yet, we are here. We are warm. We are looking up. We are wondering. And the universe, however empty, has at least permitted this much. That is the thread we still have to follow. That is the part we come to next. The part that asks, what does it mean, in the end, to be a few warm specks asking questions in an architecture of nothing? Take a breath. We are almost done. We have one more part, we are going to bring it all together. Is less than break time equals 1s, is greater than number. Part 12. By design, and it's horrifying but also beautiful. I want to recapitulate, slowly and without drama, what we have done tonight. Because we have done a lot, and the picture is, by the end, surprisingly clean. We started with your hand on a table. We pointed out that the sensation of contact is not contact. We went inside the atom, and we found that the atom is more than 99.9999% empty. We discovered that this emptiness is enforced by quantum law, by the uncertainty principle, by quantization, and most fundamentally by the Pauli exclusion principle, which forbids electrons from occupying the same quantum state and so holds open the volume of every atom in the universe. We saw that without exclusion, all matter would collapse to neutron star density, and the entire human race would fit inside a sugar cube. We stepped out from the body into the solar system, and we found that the solar system is mostly distance, a grain of sand-sized planet orbiting a basketball-sized sun in an auditorium of nothing. We followed Voyager out to the heliopause, past the Oort cloud, across the 4 light-years of vacuum to Proxima Centauri. We noticed that the space between the planets is a better vacuum than anything humans can manufacture. We stepped further out into the galaxy. We found that the Milky Way is not a glowing disk, it is a thin scattering of stars in an enormous volume of darkness, with an average separation of 5 light-years between neighbours. We noticed that the disk we see in photographs is a long-exposure illusion. We placed ourselves inside the local bubble, an empty region inside an already empty galaxy. We went out further, to the scale of the cosmic web, and we found voids hundreds of millions, even billions, of light-years across. The Boötes void, the Eridanus supervoid, the KBC void in which we may sit. We noticed that, at the largest scale we can survey, voids occupy more than half the volume of the universe, and the threads of cosmic structure are thin filaments of dark matter on which the visible galaxies ride like foam on a wave. We turned to the cosmic inventory and discovered that only 5% of the universe is ordinary matter, and less than 0.1% of the universe is in any solid form. We met dark matter, 27% of the universe, invisible to light, holding everything together by gravity. We met dark energy, 68% of the universe, a pressure built into empty space, pulling the cosmos apart and accelerating. We went inside the empty space itself and found that even the bare quantum vacuum is not empty. It is a roiling field of zero-point energy and virtual particles. We met the Casimir effect, which proved that the vacuum exerts force. We met the cosmological constant problem, the largest discrepancy between theory and observation in the history of science, a discrepancy of a factor of 10 to the 120th, suggesting that the value of the vacuum energy in our universe is precisely tuned to within a fraction of what the math expects. We took a brief detour through the holographic principle, in which the bulk of three-dimensional space may not contain anything in its own right. We added time. We met the accelerating expansion. The DESI results from this year, suggesting dark energy may be evolving. The receding sky, which will eventually leave our local group alone in a black cosmos. We projected forward into the eras of the far future, the stelliferous, the degenerate, the black hole, the dark. We met heat death. We met the Boltzmann brain problem. We met the possibility of vacuum decay. We met cyclic and bounce cosmologies, which offer a small reprieve. Now, the central claim. The universe is empty by design. By that, I do not mean someone planned it, although that's a question for a different kind of evening. I mean that the equations of physics require this. Without the Pauli exclusion principle, no atoms. Without the uncertainty principle, no quantization. Without gravitational clustering, no galaxies. Without inflation in the first instant, no cosmic structure. Without dark energy at the exact value it has, either no galaxies at all, if too strong, or a universe so flat it could not form structure if too weak. Without the precise vacuum we have, no stable matter. Each piece of the architecture is precision engineered, in the sense that the value has to be what it is in order for anything else to exist. The emptiness is calibrated, the hollow is fine-tuned, the void is a machine, and here is the paradox at the center of everything we have seen tonight. The emptiness is not the absence of existence. The emptiness is the precondition for existence. Without nearly all the volume of the universe being empty, no matter could clump, no stars could form, no galaxies could organize, no planets could orbit, no life could arise. The thing we sometimes treat as a sign that the universe is hostile to us, the overwhelming preponderance of nothing, is, by the math, the thing that makes us possible. We are the rounding error in an enormous void. But we are not in spite of the void. We are because of it. Now let me state the horror, plainly, so it earns the word in the title. Most of the universe is a place where nothing happens, where no being can form, where no signal can survive, where consciousness cannot coalesce. We live in an exception. The exception is small. The exception is shrinking. By 150 billion years from now, almost all the galaxies we can currently see will be gone from view. By 10 to the 100th years from now, the cosmos will be a thin gas at almost absolute zero, expanding forever, devoid of structure of any kind. There may be brief flickers of consciousness, Boltzmann brains, perhaps in the asymptotic dark. There will not be anything else. Anything we recognize as a story will be over by then. The universe will be empty in a way we currently cannot easily picture, even after all of tonight's practice. And yet, here we are, inside the exception. The stelliferous era, into which we have been born, is a brief, brilliant interval in cosmic history. We are inside the warm patch. We have eyes, we have telescopes. The James Webb Space Telescope, the Dark Energy Spectroscopic Instrument, the Euclid mission, and a dozen other instruments we have built with our own hands are right now, this year, in 2026, doing the work of telling us how empty the universe is, in detail, with precision, in real time. The universe has, very briefly, produced a creature that can map its own architecture. That is, if you let yourself feel it, one of the more extraordinary turns the story has ever taken. A piece of the cosmos has folded back on itself and noticed how empty it is. That is what we are. The horror is the scale. The beauty is the noticing. Both are real. Both are part of the same picture. The universe is mostly nothing, and a tiny, brief, brilliant patch of it has briefly woken up to that fact. That patch is us. We are the universe noticing. So when you put your hand back on the table, when you let go of the screen and feel the wood under your fingers, remember what we have learned tonight. You are a precisely arranged probability cloud, briefly held in shape by quantum rules, inside a body that is mostly nothing, on a small rocky shelf, in a thin glaze of warm structure, in a vanishingly small, bright patch of an enormous, structurally empty universe. The hand on the table is not touching the table. The hand and the table are mostly the gaps between their own atoms. The atoms are mostly the gaps between their own nuclei. The cosmos around them is mostly the gaps between its own galaxies. The future of all that emptiness is more emptiness. And somehow, against every reasonable expectation, the system has produced a moment in which you are sitting still in a quiet room, breathing slowly, hearing a calm voice, and turning all of this over in your mind. That the universe has rules at all, that those rules permit a moment like this one to exist, is the closest thing to a small miracle the math is willing to deliver. Maybe this is what the universe has always meant. A long quiet, a brief light, and a few minutes in which the quiet looks back at itself, and then, slowly, the quiet again. Sleep well.